So at the end of the last lecture, we introduced this golden ratio. It's a number with certain properties. Consider an interval. So we break this interval at a certain point. This gives us two ratios. The ratio and the ratio the first one is the total length over this piece. Second one is this piece over the second one. We want to check where we can make the cut such that these two ratios are the same. This gives us a differential equation. Simplify this. Under the assumption that x is between 0 and 1, we get a quadratic equation. So using the formula, we get quadratic formula. Combined with the condition, we get the solution. If we find the approximate value, we call this the golden ratio, and we will encounter this later. So today we'll go to the geometry. So to go to the geometry, we start with one-dimensional geometry. So one dimension, just a line. Okay, that's all we need. We have the direction of the axis, the origin, and unit length. With this, you can find 2, 3, -1, -2. You can find the fractions, you can find all the numbers. A very important property of this number line is the ordering property. Ordering. One is bigger or smaller than the other. Okay. So we can compare two numbers. One is big, one is smaller. You may say, okay, this is easy. We do this every day. But this is very special for this one-dimensional line. If we will introduce a two-dimensional line, dimensional space, there's no ordering over there. So this only applies, only exists. Okay. We'll emphasize this. And a related thing about this is the distance between two numbers. You can find the difference, maybe positive, maybe negative. With this called the absolute value. Okay, let me check with you. Kira, have you seen this function before, the absolute value?
Yeah.
Okay, so if the, okay, let's, Jessica, absolute value of -5, what's this?
5.
Okay, cool, okay, now we'll move on. So this is about this one-dimensional case, then we move to two-dimensional case. The big difference, no ordering anymore. Call this the two-dimensional coordinate space. D for dimension. Later you will learn this 3D space. Okay, so for now, we'll focus on the two-dimensional plane. Two-dimensional plane will have an x-axis, the horizontal one, y-axis, the vertical one. And we label this as the origin. Unit size. Okay. For any point on the plane, we can find the coordinates. Mhm. On the two-dimensional plane, we use two numbers to locate the plane. The first number, we call it the x-axis. X coordinate. Second number, the y coordinate. Every point on the plane. And the other way is also true. Given a pair of coordinates, we have a point. It's similar to what we have for the one-dimensional case. One-dimensional can have a line and a number, a point and a pair of coordinates. Given 2 points, let's pick 2 points. I'm going to mark 1 point here on there. Give these 2 points, we can find their coordinates. We can also find their displacement. So the displacement. The displacement is the change of coordinates from one point to another. So how the coordinate changed from P to Q? A notation for this will be from P to Q. We put an arrow on top of it. So this will be the displacement. We also call it a vector. So a geometric object. Now let's compare the difference of the displacement of vectors. I have one this, another displacement. These two displacements, or these two vectors, different starting point, different ending point. So we call P the starting point. Q the ending point. A vector has a starting and ending point. So these two vectors, from A to B, from C to D, can write this from A to B, then from C to D. They have different starting and ending points. However, the displacement, they are the same. In this case, we see the two vectors are actually the same. As long as okay, so this is a property about the vectors. It's only about the change. Where you start, where you finish, doesn't matter. It's only about the change. Okay. A very special case is when the starting point is the origin. Now I'm going to pick another point. If the starting point is the origin, we call this vector the position vector. Okay. So we emphasized that on the one-dimensional line, we have order. A number is bigger than another or smaller than the other. However, on this two-dimensional plane, if we have 2 points, we cannot say is bigger, which one is bigger, which one is smaller. Very important thing. No ordering. On the plane. For example, if we have 2 points, 1, 3, another point, 2 and 2. We want to see if we can see one is bigger than the other. If we look at the first coordinate, this point is bigger. But if we check the second coordinate, this point is bigger. So which one is bigger for these two? There's no logical way to say one is bigger than other. There's no ordering on a two-dimensional plane. So how do we see the relative position? Not large or small, but we have to use a direction. So in our two-dimensional case, we have this left, right, up and down. Sometimes we use south, north. Okay, let's see what in the two-dimensional plane. Sometimes we use this orientation system, north, east, south, west. For example, give me 2 points. We can see A is on the east side of B. B is on the west side of A. We don't see which one is bigger, which is smaller, but it's on the east or west side. Okay, I add a third point. Okay, now Amy, how do you see the relative position of C with respect to A?
So it's like just above A.
Okay,
It's
we can
north
uh-huh.
of
Okay,
A.
okay, yes. So we have choices. We can see it's right above A, or we can see it's north side of A. Either works. Aaron, can you see something about C relative to B?
I say that C is the north and B is the west.
Okay, so C to B or B to C?
Let's see.
Okay, let me make it more precise. BC. So which direction?
Oh, let's see. It starts from B and then to C. So B to C.
Okay, so this, we can say this
Hmm.
displacement will go east and north, so northeast.
Hmm.
Okay. Fred, can you hear me, Fred? Fred, Sophie. Okay, Fred, what do you see for B relative to C?
You mean like how to move the point C to B?
Mm-hmm. So which direction? It's the opposite of this one. It's the opposite, so we will move to the southwest.
This mean okay, this is southwest.
Mm-hmm. Okay, so now we will put them together. For one-dimensional line, we have order. For a two-dimensional plane, we have direction. No ordering. If you want to be more precise, we say no ordinary ordering. There's some special ones that are useful. Okay. Now with this, we can graph function. We set a very simple one. Peter, can you hear me, Peter? What about Sophie? That's a message. Let me check. Oh, okay. Okay, Peter, I haven't asked my question. I want to just check if you are here. If you can hear me. Okay, so Peter can hear me. Okay, Peter, how to do you know the graph of this function? Okay, yes. He answered. This is a parabola. So let's pick a few points. See how to graph this. The square 4101. 1, 4. Okay, so the graph is a parabola. Many of you have seen it before. Okay, let's graph another one. Y equals okay. So how do we graph this function? Okay, let's think about how do we graph this function? Fred, what would you do, Fred?
See, I should. We can find the like the first point maybe like for x is it is a negative 2.
Okay, so there are different ways to graph this. One of them we convert to the vertex form, complete square. I only have 3, but I add 4, so I have to subtract 1. This is called the vertex form. And this is the standard form. Okay. Why it's called a vertex? The vertex, it means we can find a point. So this give us a point, the vertex. Okay, so this is the vertex form. We have the h and the k. You can see here, subtract 2, subtract 1, so h is 2, k is -1. Let's find this point. -1. And 2. This is the vertex. Then to draw the graph, it's shifted parabola. Use different color. Okay. If we put this into the vertex form, we know where the axis is, where this point, because the vertex, then we can draw the parabola. A second way to draw this is use the factorization. Okay, can you tell me how do we factorize this quadratic polynomial? Aaron, yes.
-3 times x minus 1.
Okay. I'm going to reverse order, but it's essentially the same. So in particular, we know that this will be 0 when x is 1 or 3. Let's label this. The graph of this function goes through x1, y0, x3, y0. The graph will be something like this. A second way to graph this. Okay, with this, we want to solve the following inequality. Amy, what would you do? How do you solve this inequality?
I mean, I think it's like the same way you solve like the normal equation.
Mm-hmm.
So it has to, so x minus 1, like the factorization would be less or equal to 0.
Mm-hmm.
So x can be Yeah.
Okay, so the product of the two numbers is non-positive. That means if this is positive, this must be negative. Okay, there are different ways to do this. A more maybe simple approach, a simple approach is if we check the graph. This is the graph of the function. On the graph, you can see if x is between 1 and 3, the value lies below x-axis, then it must be negative. In particular, if x is bigger than 3, the value is positive. Smaller than 1 is negative. So we can get a lot of information about the function from its graph. If we can graph it this way, we can solve it using the graph. Then this will be the solution. Okay, a similar one. Solve. Okay, give you a few minutes to think about this. How do we solve this inequality using the graph? Enter your answer in the chat. I will check. How to solve this inequality by making observations on the graph. When will this be positive? Okay, have one, that's correct. Kira, what's your answer? Unmute yourself. Any progress, Kira?
Would it be 1 is greater than x? Oh, no, that doesn't work.
Yes, yes, but we see it the other way. X less than 1. That's
X
correct.
is less than 1.
So it will be this part. Anything else?
Or
Uh-huh.
would it be or x is greater than 3?
Yes. Okay. So we have two choices. Either x is less than 1 or x bigger than 3. Either case, the value will be positive. That's how we solve the inequality using the graph. Okay. Next, let's recall this Pythagorean theorem. I think many of you have seen it before. Pythagorean. It's about this. If we label this A, oops, not this. A, B, C. Okay, let's check. Fred, you have seen the formula before about this Pythagorean theorem of the right triangle?
We see this before.
So this A square,
Square plus B square equals C square.
yes, okay, you have seen it before, right?
Yeah.
Okay, so, and why is this? How do you prove it? Okay, let's think about it. How do we prove this? Amy, have you seen it before, Amy?
Yeah.
Okay. So I will give us some proof. What we do is we make some manipulation. I'm going to make another copy of this triangle, but this time it's rotated. And we're going to make another copy. This will be A, B, C. I make another copy. And a third copy, another color. Okay, so my drawing is not that perfect. If I have this good drawing, this should be a square. Let me label this. This will be A, B. It will be A, B. Okay, so we have C. C. Okay. So now what do we have? We have a large square. Okay, Amy, what's the edge of the square? Unmute yourself. You are muted now, right?
B plus A.
Okay, that's very nice. So large square. This will be the area. Aaron, what's the edge of a smaller square?
4C.
Edge, not the perimeter.
Oh, edge is let's see.
Just a C.
Yeah.
So edge is C, this is the area.
Yep.
Okay, the triangles. For the right triangle, let me check with Kira. Do you know the area of this right triangle?
Base times height divided by 2.
Okay,
So that'll be
Huh.
A times B divided by 2, or A times B times 1/2.
Okay. How many of these do we have?
4.
4. So 4 triangles. So the area will be A, B half times 4 to AB. Okay. All of this are very basic, nothing about the theorem yet. The observation is the area of the smaller square, C square, where combined with the area of the 4 triangles should equal to the area of the large square. Fred, do you agree? And Jessica, what do you think, Jessica? Peter, can you hear me, Peter? Okay, if not, I check with Erin. Do you agree that if I add the area of the square with the 4 triangles, I should cover the area of the bigger one? Do you agree, Erin?
Yes.
Okay, so now let's write it down. From the observation, we have a plus b squared equals c squared plus 2ab. Okay, now let's expand this. What's a plus b squared? Amy, can you expand this? The formula for the square. I'm going to write something and I will check with you. Is it correct? Could I write this? Or am I missing something? Jessica, what do you see, Jessica?
I think it works.
So we're missing the crossing term 2ab. Okay. Now we compare these two sides. We have the common term 2ab. Eliminate that, we're left with okay, so this is how we prove the Pythagorean theorem using these squares. How did we construct this big square? We start with one right triangle. I place another one over there, third one, fourth one. Total, they enclose a large square with this area. The inside, smaller square with this area. 4 triangles with this area. Then we have the equation simplify, we get the formula. Amy, question about the proof. Is this clear or there's something we should check?
I think it's clear.
Okay. So remember this graph when you prove this theorem. So if you know this construction, then you can recover the proof very easily. You will not forget this. Very useful theorem. Very maybe there are many different proofs. I prefer this one. In the homework, I will give you another solution, similar but different. Okay, so pay attention to this week's homework. Homework, another proof. Okay, so that's the Pythagorean theorem. Now we go back to our two-dimensional geometry. I have 2 points. P, Q. Okay. Now I want to measure the distance between the 2 points. So to find the distance, we will construct a right triangle. AD. Okay, so you can see this point has the same x coordinate as P. So it's on the south of P. It has the same y coordinate as Q. So it's on the west of Q. In particular, we guarantee this is a right triangle. Okay. Jessica, what's the length of this side? How do we find the length of this? This one is B, this one is D.
B minus D.
Okay, so in this case, this will be B minus D. Oh, it's a different color. And Fred, the length of this.
Of this length is C minus A.
Okay, very nice. So C minus A. Now we are going to apply the Pythagorean theorem. The square of this length will be the summation of the two squares. So the square of the length with P and Q will be okay. I wrote something wrong. You said some C minus A, but I wrote D. C minus A. Make corrections. Okay, so that's the Pythagorean theorem we just proved. Then we take a square root. Okay, so this is the formula. Let's have a short break, and after the break, we will try a few examples to find the distance between 2 points. 5 minutes break. Be back at 26. Okay, let's try some examples. 2 points. Only 2, -1, Q, 5, 3. Okay, let's find the distance between the 2 points. I'm going to use this P and the Q for the distance. Now we can say in mathematics, the same symbol, same, but it means different things in different contexts. If this is for the real number, this will be the absolute value. But if you have 2 points, that means the distance between the 2 points is not the absolute value. In the future, you may say this in different contexts, will mean different things. Where do we start? How do we find the distance? Aaron, what would you do?
I'd plot the thing out on the coordinate.
Okay, so we will apply this to the formula because this is our first example. I'm going to write down the formula. In the future, you may skip this step, but in the beginning, they make it more concise. Okay, so this will be C minus A, B minus D. In our case, C is the coordinate of x coordinate of Q. This will be 5 minus 2. Jessica, what's the second part? Unmute yourself.
Could you repeat the question?
So the first part, 5 minus 2. What's the second part?
-1 minus 3.
Okay, so this will be 1 minus 3. Okay, very good. Now we'll do some calculation. 5 minus 2, 3 square, negative 4 square. Because the square is the same as 4, so I'm going to omit this negative. Oops, that's it. Nine, 16, 25, fine. So in this way, we find the distance between the 2 points. Okay. So on the plane, we have the triangle, we have a rectangle. More generally, we have the called polygon. They may be irregular, it may be a little bit strange. Try to draw a general polygon. A polygon is a generalization. If we have only 3 edges, we have a triangle. If we have this, we have a rectangle. A polygon is just a collection of straight edges. Now we can find the length of each side. Add them all together. We call this the perimeter. Okay. Very simple object. So This can be done as long as you have a ruler. If you can find the length, you can add them easily. A very difficult thing in the history of mathematics is to find the length of of a circle. So a circle. The geometry of this is very simple. It consists of points with the same distance. Pick this, we call it the center. Let me draw a circle, see if I can draw a good one. And I will redraw this. What's the geometry of this circle? It consists of points whose distance to a given point are the same. P. Okay. What does this mean? That means this collection of points whose distance okay, words and formulas mean the same thing. Any point, if the distance is not r, it's not included. Any point, the distance is r, then it's included. Put them together, you get this, we call it a circle. So maybe 1,000 years ago, people know how to draw a circle. But it has been a very difficult issue to find the length of the circle. So without any technology, let's think if we were born 2,000 years ago, we have no computer, no cell phone, how do you compute this length? Aaron, what would you do?
I cut the circle in half and then cut that line that divides the circle in half.
Okay. So first step, okay, Aaron, you cut this in half. Aaron, continue.
And then I'd put that, and then I'd put a half mark in that line, so to mark the halfway point.
Okay. Let's make this A, B. This is what you mean?
No, in the middle of the line.
The middle of a line. Okay, so is it just the center?
Yeah, like okay, like where that line intersects basically as of right now.
Okay, next.
And then I draw, and then I take from that point and then draw up.
You mean from there?
Let me see.
Is this what you mean?
No. I mean only to the PO mark, the PO mark.
Okay. So you mean only to here?
Yes.
Okay, so how do we get the length of the circle?
Let's see now. Okay, that is a very good question. Let's see, circumference.
So it's not easy to get the length of a circle directly. The old generation mathematicians, what do they do? Use approximations. So we don't know the circle, but if we draw, we start with a square. I'm going to draw a square over there. Okay, it's up. We can measure the perimeter of the square. This will give us a very rough approximation of the perimeter. Okay, Aaron, how could we make this better? How could we make a better approximation?
What do you mean?
Okay, what I mean, so if I add more edge, let's use a different color. If I add, oops,
Oh, I mean, you use an octagon?
yes, yes. Very soon we will run out of names, so we will use this polygons. Each
You-
time we
You
cut,
tried regular polygon.
okay, we cut the circle using regular polygons. If you have more and more edges, we expect better and better approximations. That's what the Asian
Right.
mathematicians do. We can go one step further.
I see a 12,288 sided polygon to make the most accurate stuff.
Okay. Okay, so that's some in history. The mathematicians, they don't have a computer, so they have to do this using their hand. Who is that? So this mathematician is called Archimedes. So he used this 96 side polygon. And he found a method to find the perimeter. He showed that. Okay, circle, it will be the perimeter. This relates to the number pi. Okay, let me introduce the pi first. Okay. We'll do this later. Let's first introduce the notation that we need for this. Let P be the perimeter. Circle of radius. The observation is the ratio of the perimeter over twice of the radius or the diameter. This is constant. It's the same for all circles. So we introduce this as pi. Okay, so the logic is, so this is the same. all circles. So we set it as so the mathematicians, they want to find the exact value of pi using this method. We cut the circles or we cut the disks. This Archimedes, he found that this okay, he found a very good approximation. This is approximately so he's around 250 years BC. Very soon, a Chinese mathematician called Liu Hui, so it's 265 AD. What he does, he improved, he found a better algorithm. He can use this using a much larger number, 3072 sided. So this obtained much better approximations. And another improvement is called 组冲之. He's about 480 AD. He used this 12,288 sided polygon. So he obtained this approximation. If we find this number approximately so I check the value using a calculator. You can check this after class. Nowadays we have computers. We can check the value for pi. Some of you remember this for many digits. Okay. You can see almost 2000, not 2000, almost 2000 years ago from now, he can find this pi up to 2, 3, 4, 5, 6. The first 6 decimal places is accurate. Okay, some history about how to find this number. It takes a lot of mathematicians, a lot of maybe 1,000 of years to figure out what this number is. It's not an easy problem. Now we try to, some way we practice to remember the first 100 digits of pi. So we should also know how to find this pi. This is a useful method, very simple, but very simple to understand, but very difficult to actually compute. Okay. Okay, so this is about the perimeter of polygons and circles. Next, we go to the angles. close related to the circles. We start with a fact. The total angle of a circle. Okay, let me check if you have seen this before. Jessica, have you seen this before? The total angle of a circle.
Isn't it 360?
Okay, nice, nice. So 360. Okay, now the question. So why do we set this number? Do we pick this number? Let me draw a circle and then a total angle of this. Why? So where does this number come from? Okay, again, so this is the history of mathematics. In the old times, it's even difficult to count how many days in 1 year because in different places of the world have different calendars. At that time, people know it's approximately 360 days a year. Okay, so this is one reason. It's not accurate, but this is one of the reasons why the total angle is 360, because we want to go around this in 1 year. Okay. Now we have the total angle of a circle. Another special one is the flat angle. Amy, I check with you. What's the angle of this one?
180.
180. Okay, so this will be 180, and it's half of the total angle. We can go off the top, we can go off the bottom. Each of this is 180. A third one. Okay, and we call this a flat angle. Okay. Kira, what's this angle? We go,
90 degrees.
okay, so 90 degrees is half of a flat angle. These two parts are the same. We call it a right angle. Many of you have seen this before, a right angle. And let's see, why do we use this right? We know left, right, is this has anything to do with left or right? There's no, why there's no left angle?
Is there a wrong angle?
Okay, yes, okay. Why no wrong angle? Why do we pick this? What does it right mean?
Upright.
Okay, okay. So again, so this is the history in the development of the mathematics. So this, we have this upright direction. So this is the reason why we call it a right angle. It goes to the upright direction. Okay. Okay, some other special angles. Another special angle we go half of the right angle. This will be 45 degrees. Another one. $60 degrees. So the leftover will be 30 degrees. So why are these angles special? Why don't we consider 46? Why not 50?
Because they're related to 360.
Okay, it's because this is half of the right angle. And this is 1/3 of the flat angle. Okay, it's also related to the total angle. Okay. So sometimes we want to divide the angle equally. This can be done. So if we divide this equally, we get this. Okay. So now we have two ways to measure the angle. If we go to the circle case, one, x, y, here. Okay, we can measure the angle. Make it smaller one. Given starting, ending, direction. Okay, I cannot see through my fingers. Okay, let me make this bigger so we can measure the angle. We can also measure the length of the arc. There's a correspondence between the two measurements. The ratio is constant. Ratio. So I will use alpha for the angle, L for the length. So two different measurements. Measure the angle. starting, ending position, the angle. Starting, ending point, the length of the arc. The ratio is constant. To find this constant, we'll consider a special case, the total angle. Is and the total length will be 2 pi. In particular, we have L over alpha equal to this. So because the ratio is constant, we consider a special case when L is the whole circle of 2 pi. The whole angle 360. So the ratio is constant, is this constant. So this gives us a connection between the two measurements. We can go from angle to length, can also go from length to angles. Okay. We will have more about this next time. Any question about today's lecture? Okay, so some important stuff, and I will swing back. So it's the method to find something we don't know. We don't know how to find the length of the circle. What do? We use approximations, use something we know. And the proof of the Pythagorean theorem. Keep this picture in your mind. To prove this, we have a triangle, but we can make 4 of them. From together, we get 2 squares. Then we have the formula. Okay, so keep this in your mind. And that's the end of today's class. Let me go back to the last page. Okay, if you have no questions, and we will see you